Today I'm going to present a new write caching policy that focuses on solely utilizing non-volatile write cache for application performance. This is a joint work with Hwanju, Sang-Hoon, and my advisors Joonwon and Jinkyu. Okay, I'll begin by explaining the need for non-volatile write cache. DRAM cache is ineffective for improving write performance because of its volatility. As a result, write traffic has known to be dominant in production environments with large capacity DRAM cache. So non-volatile write cache can help to improve write performance by providing fast responses for write requests without loss of durability. The candidate cache devices include flash memory, emerging storage class memory, and battery or flash-backed DRAM. The simplest caching policy to utilize a given cache device is caching all writes without differentiation and writing back to backing storage asynchronously. This simple policy is intended to provide fast responses for all incoming writes as much as possible for improving system-wide write performance. However, the simple policy cannot fully utilize the benefit of non-volatile write cache in terms of application performance. To show the real application impact, we conducted a simple experiment using Tpcc workload. In this experiment, we used two cache devices including 32 MB of NVDRAM and 4 GB of flash SSD. This graph shows the result as underlying storage configuration changes. As you expected, the system performance represented as I/O operations per second is improved a lot by additionally using the cache devices. However, the application performance measured as transactions per minute is not matched to the system performance. Specifically, in the NVDRAM case, the simple policy achieves only the marginal gain in the application performance, despite of the huge gain in the system performance. Moreover, the application performance is significantly degraded rather than improved in the SSD case. So, what's the problem? The root cause of this unexpected result is that the simple policy makes all of the writes equally contend with each other, despite of different criticality in terms of application performance. In the following slides, I'll explain why caching policy matters in the existence of the different write criticality. Basically, the role of server applications is providing a specific service in response to a client request like a key value pull request. Consequently, the performance of request processing determines the level of application performance that a client perceives. For this reason, typical server applications delegate costly write I/O such as checkpointing and compaction to background processes or threads. So we can say that only the writes that delay the progress of request execution is critical for application performance. However, since the simple policy caches all writes without differentiation, critical writes should contend with non-critical ones for the limited capacity and bandwidth of a cache device. Okay, let's take a look at the specific problem of the capacity contention first. As shown in this example, the free blocks in a cache device can be exhausted by a burst of non-critical writes because of the speed of making free blocks is bounded by slow backing storage. So in this case, the subsequent critical writes will be stalled waiting for free blocks, and therefore the progress of request execution is delayed by slow disk latencies. And even in the case where a cache device has sufficient free blocks, a critical write can be queued behind a burst of non-critical writes, and concurrent IOs for writing back cached data updated by non-critical writes before. In this scenario, the critical write can suffer from excessive queuing delay because of the limited bandwidth of a cache device. And as a result, the application performance can be significantly degraded. To handle these problems, we propose a request-oriented caching policy that caches only the writes, delay the progress of request execution. To do so, we define critical process as a process or a thread involved in handling requests. And we also define critical write as a write awaited by a critical process regardless of its I/O characteristics such as I/O synchrony. Based on these definitions, our goal is to fully utilize the given cache device for application performance by caching only critical writes. The key challenge for realizing the proposed policy is how to accurately detect all critical writes. So to address this challenge, we need to classify which type of write is critical in the first place. Basically, the synchronous writes from critical processes are critical by definition. In addition, critical writes can be induced by process and I/O dependencies to a critical process. And this type of critical write makes critical write detection more difficult because it is not issued by a critical process, but eventually delays the progress of request execution. I'll explain more about the dependencies in the following slides. The process dependency occurs between processes. For example, the process dependency is generated when a critical process needs to acquire a lock that is held by a non-critical process. In this case, if the non-critical process issues a synchronous write within this critical section, then the critical process should indirectly wait for this write to complete, even though it is not issued by itself. Therefore, the synchronous write issued within the critical section is a critical write induced by the process dependency. Unlike the process dependency, the I/O dependency occurs between a process and an outstanding I/O. For instance, the I/O dependency is generated when a critical process F syncs to a block on the write back issued by a kernel thread for cleaning OS buffer cache. As another example, the I/O dependency is generated when a critical process attempts to overwrite a buffer page that contains critical data for file system consistency. In these scenarios, the critical process should wait for the outstanding write to complete, though the write is not issued by the critical process itself. Therefore, the outstanding write that the critical process synchronizes with is a critical write induced by the I/O dependency. To accurately detect all critical writes in the presence of the runtime dependency, the first thing we need to do is to identify a set of critical processes in an application. For critical process identification, we chose an application-guided approach, which is based on an application-level hint on a critical process. To get the hint, we added a simple interface to set or clear process criticality at runtime. Based on the given hint, the synchronous writes from critical process can be easily detected as critical writes. And for dependency resolution, we designed criticality inheritance protocols. The criticality inheritance protocols are comprised of process criticality inheritance, I/O criticality inheritance, and blocking object tracking for handling cascading dependencies among multiple processes. In this talk, I'll only explain the primitive techniques. Please see our paper for more complicated scenarios. So the process criticality inheritance is similar to the priority inheritance used in process scheduling. specifically, when a process dependency occurs, a critical process inherits its criticality to a dependent process, so that the synchronous write issued within the synchronized region can be cached, regardless of the original criticality of a requesting process. As a result, the critical process can quickly acquire the log and proceeds and do the residual work for request execution. The Io criticality inheritance is designed for resolving the Io dependency. The key issue to design an Io criticality inheritance is how to quickly resolve the dependency to an outstanding write without compromising the correctness. To handle this issue, we devised immediate reissuing and Io completion discarding as a technique for the Io criticality inheritance. In our technique, a critical process reissues the dependent write to a cache device and proceeds when the reissued write completes without waiting for the original write. Later, the result of the original write is discarded upon completion to suppress side effects like duplicated notification of Io completion. We implemented our schemes based on Linux and Flash cache, and to validate the effectiveness of the proposed techniques, we studied two popular applications, Postgres database and Redis key value store. In Postgres, backend is a dedicated process to handle a client's request, while other processes such as checkpointer and log writer carry out Io jobs in background. So we classified backends as critical processes for Postgres. Similarly, Redis dedicates a single master process to handle all requests from clients, while other processes conduct internal activities like load compaction in background. So we classified only the master process as a critical process for Redis. Our prototype was installed on a server with 2 hard disk drives and 2 cache devices, including 4 GB RAM disk and 256 GB of SSD. And in order to simulate clients, we ran a Tpcc benchmark for Postgres and the YCSC benchmark for Redis on a separate machine. We used several caching policies for evaluation. Firstly, all caches, all writes without differentiation. This policy is the default of Flash cache. And next, sync caches only the synchronous writes. We used this policy as a simple alternative for all because synchrony-based prioritization is known to as an effective method for improving system performance. And CP caches only the synchronous writes from critical processes. CP plus PI additionally caches the critical writes induced by process dependencies. And finally, CP plus PI plus IOI additionally caches the critical writes induced by Io dependencies. For Postgres, we also used while for caching only the writes related to transaction logs. Okay, I'll show the Postgres results first. This graph shows the average Tpcc throughput as the RAM disk cache capacity increases. All gradually improves the performance as the RAM disk cache capacity increases. This is because the number of write stalls is reduced as the cache capacity increases. And note here that the performance in the 4 GB case is the optimal performance in our configuration because the capacity and bandwidth of the cache device is sufficient for observing all the write traffic. And sync slightly improves the performance in the low capacities because it reduces the number of write stalls by filtering out asynchronous writes. However, Sync cannot catch up the performance in the high capacities because it does not handle the runtime dependencies induced by the asynchronous writes issued to disk. And though WAL and CP do not suffer from write stalls at all in older capacities, they cannot achieve the optimal performance due to the runtime dependencies. And the performance is further improved by additionally handling process dependencies. Finally, our scheme achieves the near optimal performance in all the capacities by resolving the capacity contention and runtime dependencies. Overall, our scheme outperforms all by up to 80% and filters out up to 72% of the writes without performance loss. Next, this graph shows the average Tpcc throughput as the SSD cache capacity increases. Unlike the RAM disk case, all and Sync achieve much lower performance than the criticality-aware policies, though they do not suffer from write stalls at all in all the capacities. This is because they make critical writes contend with non-critical writes for the limited bandwidth of the cache device. On the other hand, while and the criticality-aware policies improves the application performance by reducing the contention in the cache device. In summary, our scheme outperforms all by up to 2.2 times by resolving bandwidth contention and runtime dependencies. For Redis, we used the update-heavy workload in the YCSC benchmark with the 16 GB SSD as the cache device. This graph shows the timeline of request throughput during the workload execution. All shows the highly fluctuated pattern of request throughput because of the periodic background activities in Redis. On the contrary, our scheme shows more higher and stable request throughput. As a result, our scheme achieves 47% better throughput compared to all. In addition, our scheme also improves tail latency by eliminating the interference from non-critical writes. Specifically, our scheme achieves 13 times better latency at 99.9 percentile. These results indicate that our scheme is effective for improving request throughput as well as request latency. In conclusion, our key observation in this work is each write has different criticality in terms of application performance. Based on this observation, we proposed the request-oriented caching policy that solely utilizes non-volatile write cache for application performance. And through the evaluation with the real workloads, we validated the effectiveness of the proposed techniques. We are currently working on developing a system-level critical process identification for closed source applications. And we plan to apply the request-oriented approach to user interactive environments, considering direct user input as an external request. Thank you for listening, and I'll take questions.
Hi, this is really interesting work. I had a couple of questions. The first is, it seems like the dependencies would apply for reads as well. There was this work at FAST, I don't know, maybe it's your work, I'm not entirely sure, but where they spoke about how to derive such inter-process Io dependencies. So that's the first observation. It's not really a question, but it's an observation, which is that these dependencies apply to reads as well, right?
Yeah. Yeah.
Yes.
Okay.
Do you care to comment?
I don't. Go on. I listen.
Okay. All right. So the other thing is, I was just wondering about the failure modes for your cache.
Sorry.
Failure modes
Yeah.
for your cache, because it seems like you're writing to your storage out of order, because you're partially caching writes. So only some of the writes that are coming out of the file system go to your cache, but others don't. And so I'm just wondering, for a file system that really cares about the order in which writes are performed to block storage, if there is a failure of the cache, how would the file system handle consistency issues?
Okay. So first of all, our work currently our work focuses on only classifying write, and assumes read IO is almost of read IOs observed in DRAM cache. So we didn't specifically look at about read IOs. So I cannot tell whether the dependency problem is existed in read IOs. But actually, I have a plan to investigate more on the classifying reads as well. So.
And the second question was about the failure modes for the cache.
Yeah, actually, yeah, right. And we also assume that the cache device is reliable.
Okay.
We did not consider the catastrophic device failure. We did not consider device failure currently, so we used as a write-back cache.
Would you want to speculate what would happen if there is a cache failure?
Yeah, if there is a device failure, then the consistency problem happens, right? Yeah.
Okay, thanks.
Hi, I was wondering if you can comment on the interleaving of sort of the application level operations and then the system level operations, such as, let's say, SSD cleaning. Could you do something where you could use your input, so to understand what's important, to inform the drive in order to have it perform some background operations at a different time?
I'm sorry, I couldn't clearly get it. So
this is a right. You want to try again?
Could
Was
you?
that?
Yeah.
Can you
Repeat it? Yeah. Could you? There are other background operations that the system is going to perform, and you're informing this. It seems like you have sort of things being pushed down as to what's being written in the first place. But then in the case of, let's say, an SSD, you have other sort of background things that are being done under the covers. It wasn't clear to me whether the lower level operations are being scheduled by the drive, or whether you can provide hints to sort of say that the workload coming in, saying this is a good time for you to do some extra cleaning, for example.
So your question is about can we classify the background system activities from the Lucas execution, right?
can you use the same approach to maybe postpone garbage collection or control garbage?
Right.
Within the device.
Yeah, within the can you push? The garbage collection. It sometimes is a critical operation, right?
Yeah,
if
right,
you don't do garbage collection, you can't do anything. But you might be able to use your information to sort of say, this is a good time to do these background activities.
Yeah, good point. So if we have an interface to notify which one is critical for clients, Lucas execution, then the device can decide the right timing for the background activities like garbage collection or other sort of things.
Yeah.
So
Yeah, we'll take it offline.
okay, thank you.